Hi everyone, welcome to day 12 of Advent of Code. In this video, I'll be going over the day 12 problem and my solution written in Python. And yeah, let's get right into it. So for day 12, we're dealing with hot springs, where the input looks like this, where this can be thought of as a sequence of 7 hot springs, where the pound sign represents a damaged spring, and the period represents an operational spring. Um, and essentially, we have this third type of input where the question mark is unknown whether it's damaged or operational. We're also given, along with each sequence, a series of numbers. The numbers represents the lengths of the blocks of um, damaged springs, um, where each block is surrounded by at least one non-damaged string. So for example, if we look at this input without the question marks, here we have a block of length 1, where it's a block because it's surrounded by the start of the line and the period. Here we have another block of length 1, and finally a block of length 3, so we have a 1, 1, 3. Again, on this next one, we have block of length 1, block of length 2, or block of length 1, a block of length 3, so we have 1, 1, 3. Here we have blocks of length 1, 3, 1, 6. And so that's the sequence we have, and so on. And so when we go to these where we have question marks, what we want to know is how many, so obviously there are different ways that we could arrange um, the damaged and undamaged springs in this sequence given blocks of this length. So in this first example, we only have one way we can arrange it. It would have to be for blocks of this size to be true, to be the case, we need to have damaged, undamaged, damaged. However, so there's only one way that we can make this work. In the second example, we know that we're going to have to we have this 3 at the end. So this final question mark must be a damaged hot spring. But for each one of these, we could have damaged, undamaged, or undamaged, damaged. Similarly for this, we have 2 options for the each, so 2 times 2, 4 options total. For this one, I'm not going to talk through it, but again, we have potentially multiple options. So for our code, we're going to need to take in a series of springs, a bunch of block sizes, and output the number the number of options for the arrangement of damaged springs. And then we'll just sum that over all of the lines to get our solution. Yeah, let's get right into the code. Yeah, so what we want to do is go through, okay, so here's our code. So what we're doing here, ignore this line for now, but in part 1, what we're doing is very simple. We have our total, we're going for each line, parsing the springs and the blocks. We're again parsing to integers, and then we're incrementing the total by the return value of this count options function, which takes in springs. Let's just go up to the function. Takes the series of springs, which is a string, so that would be this part, and then the blocks, which is a tuple of integers, so like 1, 1, 3 for this example. Now, the way I've implemented this function is recursively solving for the number of options by sort of iterating over the string. So let me just go through how that's going to look in a couple of these examples, and then we can talk in more detail about how it's implemented. So for example, we want to go through the string, and for each time we have a question mark, we can sort of branch off into considering what if this was a period, and what if it was a pound sign. So what if it was undamaged or damaged, and then compute how many options we have from there. recursively. And so here we can either, at this question mark, we can either have undamaged or damaged. If it's damaged, so if it's a pound sign, then we know based on, since we have a block size 1, that the next value must be a period, undamaged. Then we get to this next question mark. We could try a period, but then we would only have a block of length 1 and a block of length 3, so this would be invalid. We can also try a pound sign, in which case it would be valid, so we have at least one option. Going back to the start, we could put undamaged here, then we could look here, so this would be like recursive calls of the function. This could be, if it's damaged, then we know this would have to be undamaged because we have block length of 1, and so that would also not be valid because we'd have a 1 of length 1 and 1 of length 3. Similarly, if this is undamaged, then we look here, and we're just not going to get a valid solution. So there's only one valid solution here. Let's just go through the code so we can sort of see how this is actually implemented. So the recursive function, first we have our base case. If not springs, so if the string is empty, essentially if we've gotten to the end of a sequence, then we want to see if there are blocks remaining. So if we make it to the end of the sequence and we still need to find additional damaged springs, then we should return 0. If blocks is empty, that means we've already processed all the damaged springs, and so essentially everything is matched up, then that's like one option. We found like a valid solution. Now we can sort of branch off into each of the options for the first character in the string. So if it's a dot, an undamaged spring, essentially we can just ignore it and continue from the next character. If it's a pound sign, a damaged string, this is going to be the most complicated case. First we check if there are still blocks, because if there are no blocks, then we know that this can't be invalid. For example, if because like if in this case our blocks was just 1 1, there was no 3 at the end, and then we iterated to find this, we would know that that's invalid because we've exhausted all of the blocks of damaged springs, but yet we found more in the input string. Then we can check if the length of the string of the springs is less than the amount of blocks than the size of this first block or the next block. In that case, there's also not going to be room for this final block, and so we can return 0. Returning 0 is essentially saying this is an invalid option, or like an invalid configuration. Then we can iterate over the item or the items in the block, over like the springs in the block, and we need each one of them to be damaged. Since we know that the first one is damaged, we can sort of continue along, and we need to know that each one is damaged. Finally, we can check sort of the character at the end of the block and need to make sure that the following character is an undamaged spring, so the block is the correct size. So if the length of the spring sequence is the same size as the block, then we can essentially recursively call with an empty string, because this means that the block takes up the final part of the string. So you can imagine if our string was, if springs was just this and blocks was just this, then we would return the empty string, and then blocks, this like we'll do like any subsequent blocks. So we could also do a check here, like instead of this return statement, if blocks is greater than 1, return 0, return 1. But I thought just recursively calling this and then having it be addressed in the base case here was simpler. Finally, if this character after the block is a damaged spring, then we should again return 0 because it's invalid. Finally, if none of these conditions are true so far, we know that we have a valid block, and so we can recursively call again by going to the end of the block. So here, like, we would have a valid block to start, so we'd call again from here, and we'd skip this. Then we'd remove this first element in the tuple, the block size tuple, and so we'd call with this is the springs and this is the block size. Finally, if the first character is neither a period nor a pound sign, we know that it's a question mark. In this case, this is how we actually count like more than one option. Like here in each one of these strings, since there aren't any question marks, this string is either valid or it's not. A question mark gives us the choice, and so we're potentially counting more options. So I create two variables here. The first is the number of operations if this first string is operational. The number of options, sorry, if this first string is operational. The second is the number of options if the spring is damaged. And what we can do here is essentially we're just setting, Python strings are immutable, so we're needing to set, we're calling again, creating a new string where this first character is instead of a question mark, a period, or a pound sign. And then we return the sum over these two branches. That's probably, unless you're some genius of recursive functions, that is probably hard to understand. I definitely recommend, if that didn't make total sense, to try this yourself. Either look at my code, look on the Reddit for ways people have implemented this. It's all going to be pretty similar, but the way they've structured their cases might be a little bit different. And so actually, yeah, print out some stuff as you're going through to sort of see how the function call stack is working, because it's hard just by visual inspection to tell everything that this is doing. But yeah, that's going to work for part one. And let's just run that. And we see 6852, and that's correct for part one. Now, looking to part two, the problem remains essentially the same, with one small wrinkle, that there are actually 5 copies, like each sequence of springs is actually like 1/5 the size it actually should be. So, I mean, we can just go through the example I give. This row, where like this is the number of springs, we essentially copy this 5 times and put a question mark in between. And then for the block sizes, we just repeat that 5 times. And so what that does is it gives us inputs that are 5 times bigger, but doesn't change the gist of the problem. Let's go into solving that. Part 2 here. This is almost exactly the same. We're just, when we get the blocks, we are repeating that 5 times, and when we get the springs, we are we are joining that 5 times with on a question mark in the middle. Then it's exactly the same. We're just using the same function to count the options. We just have longer inputs. And sort of the key thing that makes this computationally efficient is something I glossed over at the very start, which is this functools.cache decorator. What this is doing is it's called memoization. Whenever we call this function, it first invokes this wrapper layer, this cache. It checks if we've called the function with these arguments before. If we haven't, we just compute the function as normal. However, at the end, before we return to the outer function, we store the inputs and the outputs in like a dictionary, a key value store, so that the next time we call with the same inputs, we get the same outputs. or we don't have to like run the whole function. And so since this is a recursive function and we can get like very deep call stacks, some of these calls can take a really long time, and so this just makes it much more efficient. Um, Notably, this works because this is a pure function. It only depends on the inputs. It's deterministic, no side effects. Um, but yeah, if we comment this line out, we can see that part one will still run, but part two, it's going to take forever. I'm not sure if we'll ever get a solution in a reasonable amount of time. So this line is really essential, this cache and memoization. We can see there it runs in less than a second. So all right, that'll do it for day 12. Thanks for watching. If you have any questions or comments, please leave them in the comment section below and follow for more updates. I'll continue to be releasing a video for every problem. Thanks.